I do groundwater detectors. How to analyze the results? There are three key aspects. The first is the basics of finding water. The second is the basics of reading images. The third is how to improve the accuracy of the water detector. The basic geological knowledge of finding water. It includes four key aspects. First, the definition and basic elements of groundwater. The second is a prerequisite for building an aquifer. The third is pore water, fissure water, and karst water. And the fourth is the existence form of groundwater. Groundwater is a general term for different forms of water that exist in soil and rock voids underground, mainly including the following. First, aquiferous medium. In nature, rocks and soils have pores, fractures, or cavities of various shapes and sizes, some of which contain water while others do not. The porous media that are permeable and saturated with water are typically referred to as aquiferous media. Second, aquifer refers to a rock layer that can store groundwater and allow the groundwater to flow out under natural conditions or artificial circumstances, such as sand layers, gravel layers, etc. It generally shows a blue-purple color with low resistivity. Third, aquiclude refers to rock layers that neither yield nor transmit water, such as igneous rocks, metamorphic rocks, and shale with poorly developed porosity. It generally shows a red color with high resistivity. Necessary conditions for forming an aquifer. There are three necessary conditions. First, water storage space, voids such as pores, fractures, and dissolution cavities. Second, water storage structure, an underground formation that holds water. It is characterized by the presence of an aquiclude layer below and impermeable boundaries in the horizontal direction, which help to contain and trap groundwater. Third, good groundwater recharge. There are three of type aquifers: porous aquifers, fractured aquifers, and karst aquifers. Pore water, stored in pore of loose sedimentary rocks. Fracture water, stored in bedrock fractures. Karst water, stored in cavities of soluble rocks. Existence form of groundwater. The existence forms of groundwater are divided into bound water and unbound water. As shown in the figure, the groundwater that can move freely under the influence of gravity is the type we are looking for. Water flows downward and changes with the local overall groundwater level. Sometimes water can be struck at a certain depth, while other times it may not be. However, during the decline of the groundwater level, certain low-resistance anomalies, such as capillary water, may appear. These anomalies are typically displayed as low-resistance blue and purple on the image. In such cases, drilling wells may not necessarily yield water. Basic knowledge for graph analysis. Three key points are: first, a drillable, productive underground water source must have a substantial water supply. Second, identifying aquifers and aquicludes on the graph. Third, determining aquifer depth based on hydrogeological conditions. The figure shows a large-scale hydrogeological schematic diagram. This diagram shows three zones. In most cases, wells drilled in valleys yield more water than those drilled on mountaintops. However, groundwater may also be present in Zone I. Therefore, for sustainable extraction, groundwater must have a recharge source from a specific direction or from all directions. Alternatively, the aquifer's water-bearing volume must be sufficiently large. Water is stored in cracks, fissures, and karst formations. Therefore, for a sustained flow, these underground waters require significant recharge and ample storage capacity, such as interconnected fissures and fractures, allowing inflow from multiple directions. The goal of our drilling is to establish a year-round water source. How do we identify aquifers and aquiclude on the graph? This profile shows a depth of 400 meters, with measurements taken at 10 points. The spacing between measurement points is user-defined. Assuming a 10-meter spacing, The 10 points cover a distance of 100 meters. As we mentioned earlier, the red area is the aquiclude. The red area encloses a central blue-purple zone representing an aquifer. This aquifer is relatively deep, potentially around 120 meters. A lighter blue-purple zone above also represents an aquifer located at a depth of 60 to 80 meters. Which of these two aquifers should be targeted? The optimal choice depends on local geological conditions. As we are targeting gravity-driven water, in the absence of specific geological data, deeper aquifers are generally preferred. That is, the 220 meters aquifer. This range may be 200 meters, or it may take 380 meters for water to emerge. According to the local hydrogeology data, if the local groundwater is abundant, wells can be drilled up to 160 meters or even 80 meters to release water. In areas with limited groundwater, reaching productive zones may require drilling to depths of up to 300 meters, while the blue-purple zone between 60 and 80 meters contains water. It is primarily capillary water and therefore not readily extractable through conventional drilling methods. How to judge the aquifer depth according to the hydrogeological environment conditions. The same blue-purple low resistivity areas in different regions, different geological conditions, may not necessarily be aquifers. Taking the image in the previous section as an example, Shanghai has abundant groundwater. If measured in Shanghai, a distance of 60 meters is enough for water to flow out. However, in northwest China, where water resources are scarce, the same depth of 60 meters may not yield water. Hydrogeological conditions vary regionally, resulting in different analytical interpretations. Therefore, as mentioned earlier, when local hydrogeological data is limited, drilling to the deepest aquifer is the preferred strategy. Abundant groundwater. This image shows that the blue-purple areas represent unconsolidated geological formations containing aquifers, which exhibit low resistivity anomalies. Where is the aquiclude located? Based on the principle of gravity flow, we expect the aquiclude to be situated below the aquifer. Therefore, we identify the potential drilling location between measurement points 5 and 7, targeting the lowest point of the aquifer. The length or density of the measurement profile is important. Groundwater that can be extracted through drilling and provide a sustainable supply must have a recharge source, either from a specific direction or from all directions. Alternatively, the aquifer's water-bearing volume must be sufficiently large. Therefore, the length and point density along the profile's x-axis are very important. Fewer points require wider spacing, and higher density requires a longer profile. How to improve the accuracy of the water detector. First, how to process the non-ideal results. Second, match the latest data processing method and remove the interference data to the maximum. Third, comparison between old and new data processing method. Fourth, fully automatic AI analysis function. These images are suboptimal. There may be interference or incorrect data processing. Free update to the latest version of iDo app. How to prevent image distortion. Enhanced data processing now allows parameter configuration tailored to specific device models. This effectively mitigates interference and eliminates spurious anomalies, and integrates AI analysis technology for 24/7 automated online analysis. Furthermore, it tracks analysis accuracy, enabling the system to continuously learn and enhance its accuracy with ongoing use. Comparison between old and new data processing method. The known well is between 0.2 and 3. The groundwater outlet depth is about 160 meters. The two graphs on the left and right are based on the same data source, but obtained by different data processing methods. Under the old processing method, drilling area ranges from 0.1 to 0.7. However, the large and distinct blue-purple zones make precise decision challenging. The new processing technique shows a clear low impedance anomaly at 0.7, facilitating easy selection of this location. We can also choose between 0.2 and 0.3, but choosing to drill between points 2 and 3 may require drilling below 160 meters before water can emerge, but 0.7 only needs to be drilled to about 50 meters to possibly water. Another set of data. Old data processing method gives the large area blue-purple. This may be caused by interference. We are unable to determine where to drill, but the new way is much clearer. It shows a distinct spot with low resistance at 0.5. That's a good sign of water, so 0.5 will be the choice. There's definitely no good reason to pick 0.5 with the old way of processing the data. Fully automatic AI analysis function. We've incorporated AI-driven analysis into the product. It gives drilling suggestions right on the image. It shows you where and how big the drilling area should be. This image shows two places to drill. Both spots are located between 0.5 and 0.7. One spot is 130 to 140 meters deep. The other is 170 to 190 meters deep. This AI tool works in 8 languages at present. Anyone around the world can use it for free around the clock. And the more you use it, the better it gets. This is a case study of AI analysis. This water source is pretty close to the surface, only 4 to 8 meters down. This data is from tests done in Shanghai. In Shanghai, you usually only need to drill about 10 meters to hit water. So, the AI's prediction is pretty spot on here. In the new software version, we have also added 3D and 3D slice views. These advanced graphics provide clearer analysis of underground structures.